Download this code from codegive.com, link in the description below. Dpsd 1, Encoding Binary Data into Hamming Code, a comprehensive tutorial. This tutorial will guide you through the process of encoding binary data into Hamming code using the Dpsd 1, Data Processing System Design, 1, convention. We'll break down the theory, explain the steps, and provide a Python code example to solidify your understanding. 1. Introduction to Hamming code ****. Hamming code is a powerful error detection and correction technique used in digital data transmission and storage. It works by adding redundant bits, parity bits, to the original data. These parity bits allow the receiver to detect and correct single-bit errors. Key advantages **** single-bit error correction * can correct single-bit errors, ensuring data integrity. Error detection * can detect, but not necessarily correct, double-bit errors. Relatively simple implementation * easier to implement compared to more complex error correction codes. Limitations overhead introduces overhead due to the addition of parity bits, increasing data size. Limited error correction capability primarily designed for single-bit errors. For multiple-bit error correction, more sophisticated codes are required, example Reed-Solomon. 2. Understanding Dpsd 1 convention ****. The Dpsd 1 convention is a specific implementation of Hamming code with particular rules regarding the placement and calculation of parity bits. While the core principles of Hamming code remain the same, Dpsd 1 specifies these details. Here's what you need to know. Parity bit placement parity bits are placed at positions that are powers of 2, 1, 2, 4, 8, 16, etc. These are also referred to as check bits. The remaining positions are filled with the data bits. Parity bit calculation each parity bit checks specific data bits. The parity bit at position 2 sub n/sub checks all bits whose position has a 1 in the 2 sub n/sub place of their binary representation. Even parity the parity bit is set to either 0 or 1 to ensure that the total number of ones, including the parity bit itself, in the set of bits it checks is even. This is known as using even parity. 3. Steps to encode binary data into Hamming code, Dpsd 1. Let's illustrate the process with an example. Suppose we want to encode the data 10110001. Step 1. Determine the number of parity bits, r. We need to find the smallest integer r such that 2 sub r/sub equals m plus r plus 1, where m is the number of data bits. In our example, m equals 7. Let's test values for r. R equals 1, 2 sub 1/sub equals 2 equals 7 plus 1 equals 9, false. R equals 2. 2 sub 2/sub equals 4 equals 7 plus 2 plus 1 equals 10, false. R equals 3, 2 sub 3/sub equals 8 equals 7 plus 3 plus 1 equals 11, false. R equals 4, 2 sub 4/sub equals 16 equals 7 plus 4 plus 1 equals 12, true. Therefore, we need r equals 4 parity bits. Step 2, determine the total length of the Hamming code, n. The total length n is the sum of data bits m and parity bits r, n equals m plus r. In our example, n equals 7 plus 4 equals 11. Step 3, position the parity bits *. Place the parity bits, r1, r2, r4, r8, at positions that are powers of 2, 1, 2, 4, and 8. Fill the remaining positions with the data bits. We'll represent unknown values with underscore. Step 4, insert the data bits asterisk. Insert the data bits into the remaining positions. Step 5, calculate the parity bits asterisk. Now, calculate the parity bits based on the Dpsd1 convention, even parity. Asterisk R1, position 1 checks all bits whose position has a 1 in the least significant bit of their binary representation, 1, 3, 5, 7, 9, 11. Asterisk bits checked, 1, 3, 5, 7, 9, 11, R1, D1, D2, D4, D5, D7. Asterisk values, underscore, 1, 0, 1, 0, 1. Asterisk to achieve even parity, the number of ones must be even. Currently, there are 3 ones, 1, 1, 1. Therefore, R1 must be 1 to make the count 4, even. Asterisk R1 equals 1. Asterisk R2, position 2 checks all bits whose position has a 1 in the second least significant bit, 2, 3, 6, 7, 10, 11. Asterisk bits checked, 2, 3, 6, 7, 10, 11, R2, D1, D3, D4, D6, D7. Asterisk values, underscore, 1, 1, 1, 0, 1. Asterisk currently, there are 4 ones, 1, 1, 1, 1. Therefore, R2 must be 0 to keep the count 4, even. Asterisk R2 equals 0. Asterisk R4, position 4 checks all bits whose position has a 1 in the third least significant bit, 4, 5, 6, 7. Asterisk bits checked, 4, 5, 6, 7, R4, D2, D3, D4. Asterisk values, underscore, 0, 1, 1. Asterisk currently, there are 2 ones, 1, 1. Therefore, R4 must be 0 to keep the count 2, even. Asterisk R4 equals 0. Asterisk R8, position 8 checks all bits whose position has a 1 in the fourth least significant bit, 8, 9, 10, 11. Asterisk bits checked, 8, 9, 10, 11, R8, D5, D6, D7. Asterisk values, underscore, 0, 0, 1. Asterisk currently, there is 1, 1, 1. Therefore, R8 must be 1 to make the count 2, even. Asterisk R8 equals 1. Step 6, final Hamming code asterisk. Now, substitute the calculated parity bits into their respective positions. Therefore, the Hamming code for the data 10110001 using Dpsd1 and even parity is 101001111001. 4. Python code example asterisk asterisk. Here's a Python implementation of the Hamming code encoding process using the Dpsd1 convention with even parity. Explanation of the code asterisk. 1. Calculate underscore parity, data, parity underscore bit underscore indices, asterisk. Takes the Hamming code data, as a list of characters, and a list of parity underscore bit underscore indices that the parity bit at this position covers. Counts the number of ones in the specified indices. Returns 0 for even parity, even number of ones, and 1 for odd parity. 2. Hamming underscore encode, data, asterisk. Takes the binary data string data as input. Calculates the number of parity bits are required using the formula 2 sub r/sub equals m plus r plus 1. calculates the total length n of the Hamming code, n equals m plus r. Initializes a list Hamming underscore code of length n with underscore placeholders. Iterates through the positions of the Hamming underscore code. If the position is not a power of 2, i.e., not a parity bit position, it fills the position with the corresponding data bit. Iterates through the required parity bits R to calculate their values. For each parity bit, determine parity bit index with formula 2i, 1 with I iterating through the range from 0 to R1. Iterate through Hamming underscore code positions to generate a list of the positions that parity bit will check. Call calculate underscore parity, to determine value of parity bit. Assign the parity bit at its calculated index. Finally, it joins the elements of the Hamming underscore code list into a string and returns the complete Hamming code. 5. Decoding Hamming code, error detection and correction. Decoding a Hamming code involves verifying the parity bits to detect and correct errors. Here's a simplified outline. A full decoding implementation is beyond the scope of this tutorial but can be built upon this foundation. 1. Recalculate parity bits asterisk at the receiver. Recalculate the parity bits based on the received Hamming code. Use the same method as in encoding, Dpsd 1, even parity. 2. Syndrome generation asterisk create a syndrome by comparing the recalculated parity bits with the received parity bits. A common way to do this is to XOR the recalculated parity bits with the received parity bits. The syndrome is a binary number where each bit represents the result of the parity check. 3. Error detection and correction asterisk. Asterisk syndrome equals 0 asterisk no errors detected. The data is likely correct. Asterisk syndrome equals 0 asterisk an error has been detected. Asterisk syndrome as error position asterisk if the syndrome is a power of 2, it could indicate an error in the parity bit itself, though you might ignore this in a simple implementation. Asterisk syndrome as error position asterisk the syndrome value, interpreted as an integer, represents the position of the bit in error. Flip the bit at that position, 0 becomes 1, 1 becomes 0, to correct the error. 4. Extract data asterisk after error correction, if needed, extract the original data bits by removing the parity bits from the Hamming code. Example of error correction, conceptual. Let's say we receive the Hamming code 101001111011. One bit is different from our encoded example. 1. Recalculate parity asterisk, steps omitted for brevity, but we would recalculate R1, R2, R4, R8 based on the received code. 2. Syndrome asterisk after recalculating, suppose we find asterisk recalculated R1 is 0, received R1 is 1-x or result is 1. Asterisk recalculated R2 is 0, received R2 is 0-x or result is 0. Asterisk recalculated R4 is 0, received R4 is 0-x or result is 0. Asterisk recalculated R8 is 1, received R8 is 1-x or result is 0. Syndrome equals 1000, binary, equals 8, decimal. 3. Error correction asterisk the syndrome indicates an error at position 8. We flip the bit at position 8, changing 1 to 0. The corrected code becomes 101001100011. 4. Extract data asterisk remove the parity bits to obtain the original data. Important considerations asterisk. Asterisk multiple errors asterisk Hamming code is designed to correct single bit errors. If there are multiple errors, the decoding process may lead to incorrect data correction or may even introduce new errors. In these cases, the receiver will have to request the information to be retransmitted. Asterisk error detection versus correction asterisk Hamming code can detect more errors than it can correct. It can detect up to 2-bit errors, but can only correct 1-bit errors. 6. Conclusion ***. This tutorial has provided a comprehensive overview of encoding binary data into Hamming code using the Dpsd convention. We've covered the theoretical foundations, the encoding steps, and a Python code example to illustrate the implementation. Understanding Hamming code is a crucial step in learning about error detection and correction techniques in data communication and storage systems. While decoding can be complex to implement perfectly, understanding the principles outlined here will provide you with a solid foundation. Remember to consider the limitations of Hamming code and choose the appropriate error correction technique based on the specific requirements of your application.